So we're going to talk today about resonance, which is an important and kind of fascinating concept in chemistry, especially as it relates to learning about Lewis structures. So to start with, let's look at the Lewis structure for a polyatomic ion called carbonate. So I've already developed this Lewis structure, but if I hadn't developed it yet, remember what I would want to do. I would want to total up the number of valence electrons, but I would have to actually add an additional 2 to account for the fact that it is a -2. It has a -2 charge. And then I would want to consider possible arrangements. I would put carbon at the center because that's where carbon likes to be, plus it is the least electronegative element out of the three. And then I would start connecting by single bonds and filling valence shells with lone pairs. And eventually I would see I need a double bond somewhere in there in order to not use more than the total number of valence electrons, but also to use all. So we have a Lewis structure, and Lewis structures are a good way to, in a two-dimensional sense, represent molecules and then use those molecules to predict their geometry, their actual three-dimensional structure, by applying VSEPR theory and our knowledge of bond lengths and things like that. So we have a prediction of the carbonate polyatomic ion. The word molecule isn't as appropriate because it is charged. So we have a prediction of what this molecule, I just did that, what this polyatomic ion looks like in space. And that prediction would be something like this. We would expect it to have one short bond length and two long. So the bond length refers to just how far apart these atoms end up being from each other in the structure. And single bonds are the longest, and then we get double a little bit shorter, and then triple shorter still, because they have to get closer and closer to share even more orbital space. So the prediction we have for this structure, based on the Lewis structure that we've drawn, would be that we expect to see one short bond and two longer. When we go and we actually go through the actual testing to see this, so this might be X-ray crystallography or some of the other methods for this, we discover that it actually has three bonds of equal length, so that the carbon to oxygen bond is equal in all three, and it is neither as it is shorter than a single bond. So a single bond would expect maybe, obviously not this, it would be like in nanometers, but if this is a single bond, it's shorter than that, but it's not as short as a double bond. It's almost like a 1.5 bond. So what is going on here? Well, first of all, obviously, the Lewis structure does not match reality. We have a limitation of the model. And anytime we're using a model, there's usually some degree of limitation to it. And this is one of the limitations for Lewis structures, is for some, actually really for a lot, but for some molecules and polyatomic ions, the prediction that we would have from them doesn't match reality. So we don't have a double bond and two single bonds. So there's something more going on. And what it's believed to be is that the electrons in these electrons here are delocalizing, which essentially, I kind of think of it as leaving the nest. They are not staying necessarily right here, but they're moving then between these three. They're not associated with a particular bond or a particular atom. They have delocalized, so they have unlocalized. They were localized here. And so our model and our reality don't fully match up. It's some mix of bonds. So this is what we're talking about when we talk about that word resonance. So let's look at some different ways to describe resonance. So first one, when you have multiple Lewis structures with the same arrangement that can be drawn for a particular molecule or polyatomic atom. And that same arrangement is really important because we don't want to confuse resonance with structural isomers. In the structural isomer, you actually have different connectivity. Like this carbon is connected to an oxygen in this molecule, but in this molecule, this carbon is connected to something that is then connected to an oxygen. So they have to have the same chemical formula, but they're not connected in the same pattern. With resonance, we do have connection in the same arrangement, so that's really important. Another way, so here's a textbook definition for resonance. Resonance describes the fact that electrons are delocalized in some molecules and polyatomic ions, or flow freely through the molecule. So that's kind of another way to think of the word delocalized, which allows multiple structures to be given possible for a given molecule. So again, let's look at that polyatomic ion carbonate. So we have our Lewis structure here. Well, the electrons that are in this double bond pair between the carbon and the oxygen, they have the ability to move. And electrons do move, right? That's why it's so difficult to talk about exactly where they are. So they could move up to this top oxygen, right? And in doing that, they would create essentially a space around the carbon because carbon's valence shell wouldn't be filled. And these electrons, the lone pair on this negatively charged oxygen at the bottom, could move to kind of fill that, but by changing that single bond to maybe a double bond, and we would get this structure instead. Again, it's the same overall thing. We have the same number of valence electrons, we have the same charge to the atom, we have the same arrangement, still carbon bonded to these 3 oxygens, but because of the movement of electrons, we have a slight change in our Lewis structure. So these Lewis structures aren't identical because we have a movement of electrons. And because electrons can move, that's like a possibility. What we really actually get is we get 3 Lewis structures that we could draw for the carbonate polyatomic ion. We can draw this one, or this one, or this one. So whenever you have that, we have 3 Lewis structures that we could draw that have the same arrangement and differ only in location of electrons. You're probably dealing with a molecule that exhibits resonance. So I want you to notice a couple things. Move myself out of the way here. They have the same charge, meaning they have the same total number of valence electrons. They have the same connectivity. That's what differs them from like structural isomers. They differ only in the arrangement of electrons, only in that. And a really important thing to remember is carbonate actually doesn't exist as any one of these, nor does it switch between them. That's kind of a common misconception. Oh, it just rapidly switched between them. I think that's the arrow's fault, but we've just chosen to show it with the arrows that way. That is actually conventional. They don't switch between them. They actually exist as none of them. Not one of these is fully accurate. Like I said, in reality, we don't see two single bonds and 1 double bond. We see essentially a 1.5 bond because the electrons have delocalized and are moving really between these 3. And so it's not that any one of them is existing at any time, it's that none of these Lewis structures actually portray accurately the way the polyatomic ion carbonate exists in nature. And that's what we mean when we say an element or a molecule exhibits resonance. It doesn't quite match our model. We still use our model recognizing that limitation. So how can I tell if a molecule is likely to exhibit resonance? And again, molecule or polyatomic ion, but that's a lot of syllables. So I have here a molecule that does not exhibit resonance, and that would be our methane or CH4 molecule. And then again, the carbonate polyatomic ion that we've been looking. So does not exhibit resonance, does exhibit resonance. So here's some tips. A molecule can have resonance structures when it has a lone pair or a double bond on the atom next to a double bond. So we have a double bond here, and we have lone pairs on the atoms next to that double bond. And the reason that's a key for, oh, I can see this one has resonance, is we could redraw the Lewis structure with the same overall arrangement, but we could move that double bond around by moving electrons. We're not going to change the connectivity. We're not going to change what the carbon is connected to, for example, but we can change where that double bond is located and where those lone pairs are located. We don't go into it in our course so much, but there's a lot more we could learn about how this doesn't change the overall charge of the substance, but it can change like individual charges. We can end up with partial charges, and like I said, we end up with partial bond lengths, like 1.5. So not all of those hybrid structures contribute to the same degree to the reality, but we don't need that information for this class, but it is kind of interesting to point out. So in summary, whenever, let me move myself in the way, whenever you can draw 2 or more Lewis structures for a molecule or polyatomic ion that differ only in the location of electrons, not in the connectivity of the structure, but only in the location of electrons, the actual structure is none of those Lewis structures that you've drawn, but is really a hybrid of them all. And that is resonance.